Bom dia a todos. Estamos aqui mais uma palestra da nossa EFRAS desse ano. E hoje nós recebemos o Martin, lá da Tailândia, e ele vai falar hoje sobre a simetria na gravidade teleparalela e as ações gravitacionais. So, good morning to you all. We are here for another lecture from Martin. It's a pleasure to have him here, and he is from he's now in Thailand, and he's going to present to us a lecture on gravitational action and its symmetries in teleparallel gravity. So, Martin, it's a pleasure to receive you here, and please, the word is yours.
Okay, so thank you for invitation and for this opportunity to do my presentation here. So basically, I will be talking about gravitational action and its symmetries. And since this is a school, this will be a rather introductory talk, I hope. So basically, the idea of this talk is that, well, teleparallel gravity and teleparallel geometry is slowly approaching 100 years, although the name of the school is 100 years, but I think it's slightly less than 100 years, depending like how do you count, whether from 1920 or 1928. And this idea of teleparallel gravity became really popular in last 15 years, particularly because of all these modified gravity theories, like FT gravity, this new general relativity, and all these teleparallel dark energy models. I think in the last 15 years, there is more like 500 papers about teleparallel gravity, modified teleparallel gravity theories. And I think there is it's quite interesting topic, this modified gravity. It's quite interesting topic, but I think there is still a lot of going on just in this case when teleparallel gravity is equivalent to GR. And I think we can obtain some new insights into gravity just when we consider this case when the teleparallel gravity is equivalent to general relativity. So the goal of this talk is to focus on this GR equivalent case. And basically, I will go in this like 4 steps. Like first, I will show you what is the problem actually with the action and variation principle in the usual general relativity. Yes, because even the usual general relativity has some subtle issues with the action principle. And then I will just show you, then I will just introduce this teleparallel equivalent of GR and show how the problem of the action and action principle is solved or dealt with in teleparallel equivalent of GR, and how do we obtain these finite actions, these regularized actions. And then I will talk about these symmetries of this action, and I will explain what do I mean by that. So just the introduction is basically the variational principle and action, just a small reminder what is action and variational principle. I think the action is the most fundamental object in physics. Right? I mean, it is some integral, which has something to do with energy, some integral over the whole space-time, where this capital L is this Lagrangian density. And by minimizing this action integral, we find equations of motion for our theory. So this is the principle of the least action. And this is just a small reminder that when we do this variation, so we vary some Lagrangian which is a function of some field and the derivatives of the field. What do we obtain by this variation? Yes, we obtain this expression, which is this usually called Euler-Lagrange expression, plus this total derivative term. Then when I require that this variation of the action vanishes, so because I want to find the minima or maxima of this action functional, so then I need to require some boundary conditions, and these boundary conditions are that usually we consider these Dirichlet boundary conditions, which means that the variations of this field at the boundary is 0, because we have this additional term here, and we usually want to make this vanish, yes, because otherwise, like, this is in principle not vanishing, right? And we usually do this integration by parts using Stokes' theorem. We show that this term is equivalent to something at the boundary, and then we have to impose this boundary condition in order to cancel this. And when we cancel this, then we have just this Euler-Lagrange expression. And then when we require the whole variation to be 0, we obtain the equations of motion. And this is like very, very fundamental thing in the physics. Typically, all forces, I mean, at least all normal forces, except some like non-conservative forces like friction or something like that, we can derive from this principle of least action. And all fundamental forces are or should be derivable from this action. And this is quite interesting in general relativity, because in general relativity, this was not actually how Einstein derived general relativity. Einstein didn't write Lagrangian and derived Einstein equations from there. Yes, it's not like when you do something like a standard model of physics, like in particle physics, when you start with Lagrangians, start with some gauge symmetries, and you are deriving your field equations from there and quantizing everything. Einstein was approaching the problem of general relativity from quite different perspective. And he was led to general relativity using very physical insights about this principle of equivalence and general covariance. So he realized that if you want to implement these principles, you choose like a fundamental variable to be this metric tensor, from where you find this like a Riemannian connection, or Christoffel symbols. Yes, it's something like derivatives of this metric. Where I use this, just a small reminder, I use this notation where these circles over gammas means that these circles refer to connection, specifically Riemannian connection. So if you will see any quantity with these circles, it means that it is calculated from these gammas obtained like this, from the classical Christoffel symbols used in general relativity. And then when you do a free falling observer, like you want to have a motion of a free falling observer in the gravitational field, that is described by the geodesics of this Riemannian geometry. And then when you want to derive Einstein field equations, he basically, how he obtained Einstein field equations from this, he was just looking for something like, what is some covariant expression from tensor, most general covariantly conserved tensor that you can put on the left-hand side of the field equations, and this is the Einstein tensor. And the original paper from 1915 actually didn't contain any action or anything for that general relativity. Yes, we didn't derive general relativity from the action principle. Who did this was Gilbert. I mean, a couple of weeks or a couple of months ago. I mean, there is still a discussion who was first, but Einstein was definitely first. But Gilbert, very soon after Einstein paper, he published his own paper, which also included the variational principle. And it is nowadays often called Einstein-Gilbert action, but for some reason I call it here Gilbert action. And it turns out that this is a very unique action. Yes? I mean, it's very, very simple. It's just this scalar curvature. But if you look on it more closely, this action is a very weird action, because it contains the second derivatives of the metric. Yes? Like inside this R, that is a Riemann scalar curvature, you have the metric, derivatives of the metric, and also second derivatives of the metric. So if you would see these, you would expect to have actually fourth order field equations. But it turns out that no, you obtain just second order field equations. It's exactly because the second derivatives do only form a surface term in the action, so they don't contribute to the field equations. And that's why we have field equations which are of the second order. But there are some subtleties, which I will explain a little bit later, actually in the next slide. So it turns out that if you do this variation, and you are trying to do a variation of this Gilbert action, the Einstein field equations, yes, this part, this left-hand side of the Einstein field equations, only come from this variation of this square root of the G and g mu nu. And it doesn't come from this variation, the r mu nu. What I mean is that in principle, we should vary it fully, yes? We should also include this variation of the Ricci tensor. But how it is typically dealt with in most textbooks, like, for example, Landau-Lifshitz textbook, is that people usually use this Palatini identity, because you can show that this variation of the Ricci tensor can be shown to be equivalent like to this expression, which is some covariant derivatives of the variation of the Christoffel symbols. And then actually, since this variation of the Ricci tensor is multiplied only, is contracted, it's just a trace of this, it's contracted by the metric, then you can show that actually this expression is just a covariant, it's just a total derivative of some quantity. Okay? So it is just a surface term. And this is the reason why it is often neglected, because we say, oh, at the boundary, which goes at the infinity, we can neglect it. And actually, in principle, for the derivation of the field equation, it's true, but there are some subtle issues with this. Because actually, if you evaluate this variation of the Ricci tensor, and you properly evaluate it, so you properly vary the full Hilbert action, what you will find out is there is this variation, which gives you the Einstein tensor, so left-hand side of the field equations. And there is this plus-minus term, which contains this boundary metric and the normal vector to the boundary metric. This plus-minus depends like whether you choose your normal vector to be time-like or space-like. And then you must have also this variation of the derivatives of the metric. And this now leads to the problem, because normally what we do is we just require this to be 0. Yes, I mean, we normally implement only these Dirichlet conditions. Yes, so it means, sorry, here it should be the variation of the g mu nu at the boundary. Yes, so the variation of the metric at the boundary should be 0. But you see, it doesn't cancel this extra term here. You actually have this like a projection along this null vector of these derivatives. And if you require the derivative of the metric to be the variation of the derivative of the metric to be 0 at the boundary, this is kind of very weird conditions, because you are basically imposing both Dirichlet and Neumann condition at the same time, and this is not really consistent. So the solution to this problem was actually discovered like 50 or 60 years later, first by York in 1972, and then properly by Gibbons and Hawking in 1977. They just basically thought about it like, if you don't want to have this weird variation also of the derivatives of the metric at the boundary, and you don't want to require that to be 0, what you can do is you can add some boundary term, which is nowadays called Gibbons-Hawking, or often Gibbons-Hawking-York boundary term, which is just a trace of the extrinsic curvature of the boundary. You add this to the Hilbert action, and then you have field equations. You derive field equations by requiring only Dirichlet boundary conditions. So you require only this variation to be 0 at the boundary, and you don't have to require this variation at the boundary to be 0. It is because the variation of this Gibbons-Hawking-York boundary term completely cancels the variation of this, completely cancels with this extra term which we have here. And this is like how usually this problem has been treated. Yes, we add this Gibbons-Hawking-York boundary term, and then our variation principle is well posed and well defined. But there are some small subtleties with this, and there are some problems with this. One problem is actually with the case of null boundaries. When we have a null boundary, then the problem is that this null vector doesn't have to not properly defined. And the second problem is we have asymptotically flat solutions. What we want to do is typically we want to just take like our boundary and just set it to infinity. Yes? Like I imagine that I have a boundary and I just send it to infinity, and this should correspond to a simply flat spacetime. But if you do this, like let's say you do this just for the Einstein-Hilbert action, this is Gibbon-Hawking boundary term for the Schwarzschild solution, you will find out that this diverges. It's infinite. So the proposal by Gibbons and Hawking in '77 was that what you have to do is this background subtraction. Basically, calculate, you introduce some reference or background spacetime, which is some flat spacetime isometrically embedded in this full spacetime, which is not always possible to do. And then you subtract the action for this reference spacetime or this background spacetime from your final action. And you find that finite action is then obtained exactly like this. You have the Gilbert action for the metric plus the Gibbons-Hawking boundary term for your metric minus the Gibbons-Hawking boundary term for this reference or background metric. And this leads to a finite action. So this is exactly the finite action, which is used in black hole thermodynamics, or when you do some like quantum gravity, particularly if you are trying to do this Euclidean quantum gravity. So this is exactly the action which you are having there. But it's always a little bit weird, yes, because you have these extra terms which you add there to cancel the variation of something. Then you have this reference non-dynamical background metrics there, which sounds a little bit weird, at least for me, like when I had first seen this. And my idea is to show you how this works in teleparallel gravity, or what's new in teleparallel gravity. So before I go to teleparallel gravity, I'll just do a small reminder that normally, like all these which I have shown, as that deals with the standard metric formulation of GR. Yeah? So this is what we usually have with the standard metric formulation of GR, where your variable is metric, spacetime metric, and you have these crystal symbols. But what you can also do, and it's still just general relativity, you can also consider these tetrads or frame vectors or field binds or fear binds to be your fundamental variables, and they are related to your metric by this relation. So in some way, this tetrad can be viewed as some kind of square root of your metric. Yes? And then you have these two kind of indices, this mu, these Greek indices. They are like a space-time indices which run from 1 to 4, and these A and B are these tangent space indices, which also run from 1 to 4, or from 0 to 3, depends how you do it. And this eta AB is just a flat space-time metric. And basically the idea is that each of these tetrads represents like the frame, like the locally Lorentz frame of some observer. And then instead of these Christoffel symbols, what you have in your theory is these Riemannian spin connections, which is Riemannian spin connections are obtained from the coefficients of anholonomy of your tetrads. And this is quite important, just a reminder that this is always possible, and this is just a general relativity. And this tetrad formulation of general relativity is used quite often, mainly by people who do like exact solutions, Newman tensor formalism, or it's also used like in supergravity because you don't need these kind of objects typically to have some spinors in your theory. So there was just a small reminder that we can also reformulate the GR in the tetrad formulation. And you can have, as far as this action which I was explaining, this Gibbons-Hawking boundary term and all this there, you can have something analogous to that in a tetrad formalism as well. Why did I introduce this? Is because teleparallel gravity is actually naturally formulated in this tetrad formalism. So teleparallel gravity, when it started, was like, I think, this first paper by Einstein about teleparallel gravity as a physical theory was from 1928. At that time, Einstein was trying to unify gravity and electromagnetism. And basically, what he did is introduce this concept of some vectors, and by vectors I mean like frame vectors of the tetrads, yes, H and U, they stay parallel at distance. So it means that when I do a, because we know that in Riemannian geometry, when I take some vector and I parallelly transport it along some geodesic, it typically will rotate. Yes? Here, it's a little bit different. You can define your connection, your covariant derivative, in a such way that these tetrads don't change, don't rotate. This is why it's called distant parallelism, right? Because they stay parallel at distance. They don't, in some sense, rotate. Which is equivalent in this modern language of differential geometry, which was not known to Einstein at the time. That is basically equivalent to having a zero-spin connection. Yes? And when you have this, from then you can trivially calculate the curvature, and you find out that, well, this has zero curvature, but such connection has a non-zero torsion. Basically, the idea of teleparallel gravity is that you use this torsion to construct some Lagrangian that leads to some symmetric field equations, and they turn out to be equivalent to Einstein equations. But this, like from 1928, I think it died very, very quickly, like this theory. And I think within like 5 years, this idea of teleparallelism was kind of considered to be very bad and inconsistent, and completely died. The reason why it actually died so quickly was because Einstein was trying to have this as a unified field theory. So he was trying, using this concept, to unify gravitation and electromagnetism. And I still don't properly, when I read this paper, I still don't properly understand like how he was trying to put electromagnetism there, because it's very, very unclear to me. I think his idea was somehow that since this tetrad has 6 extra components, he was trying to somehow establish some link between these 6 extra components, and he was trying to somehow artificially make out of it some kind of 6 components of the Faraday tensor or something like that. But yeah, that didn't work out. And because of this, because he was trying to have it as a unified field theory, it actually died completely. So, but actually around 1920 or early 30s, he was really excited about this theory, because apparently this is some newspaper article from, I don't know, 29 or 30, I don't remember which year it is, when he went to United States, and he called this like idea of teleparallelism and this unified field theory to be his most valuable theory. But it seems that he was the only one who saw that this is the most valuable theory. Because, for example, there's this quote by Pauli, who was like kind of following Einstein in this work on teleparallelism, and he was completely destroying it. He was saying like, oh, this is complete nonsense. Like such a nonsense that you cannot even, it's enough just to impress American journalists, not even physicists. So basically this idea died very, very fast in 1930s, like early 1930s, and was kind of considered like that's some weird thing which Einstein was doing in his late years. But then actually it was revived, and it was revived. I think the first paper was by Christian Moller in Copenhagen in 1961, who was trying to define this like he was searching for some like a proper definition of energy momentum and the notion of energy momentum for the gravitational field. And then he discovered that when you do this, what he was doing is he was using the tetrad formalism and looking on some kind of like tetrad analog of the Einstein, not Hilbert action, but the Einstein action. And then he discovered that, well, this is basically equivalent to this old crazy idea of Einstein. And he basically revived this theory and showed that, well, this is the theory of gravity, which is equivalent to GR, but it's not any unified field theory with electromagnetism, so there is no electromagnetism. And if you try not to have electromagnetism there, then it's actually a very good theory. It's just a theory of gravity only. And since then, it was like developed quite a lot. Yes, I mean, mainly by people doing this gravitational energy momentum problem, but then in 1970s by people like Cho, Hayashi, Shirafuji, Nakano, which started to look on some gauge theory aspects of this, because in this formalism, you can see general relativity in some kind of like a gauge theory. And then by some other people later who will trying to think about teleparallelism as some special limit of some metric affine theories. I think that was maybe the first presentation by Laura on Tuesday. And recently, this became popular because of these modified theories. And particularly in Brazil, it is still popular, but it was very popular also in the past. And I think Brazil was one of the main places where this teleparallel gravity was followed. Nowadays, it's more popular all around the world. So basically, this modern approach, what is this modern approach? Is don't take this distant parallels condition of Einstein and show that your connection has zero curvature, but a little bit twist this approach. Take a connection and define it by this condition of zero curvature. Yes, we call it nowadays teleparallel condition. And if you do this, then you find out that the most general connection is not zero connection, zero spin connection, but it's this pure gauge connection. And when you require more like metric compatibility, so it is like to be this spin connection to be antisymmetric in these algebraic indices, then you will find out that this pure gauge connection must be constructed out of local Lorentz transformations. And this is what we nowadays call teleparallel spin connection. So the physical meaning of this teleparallel spin connection is that why we call it pure gauge or purely inertial connection, because, well, look, these metrics of local Lorentz transformation, yes, this is like 3 rotations and 3 matrices, 3 rotations and 3 boosts. So the thing, yes, this spin connection depends only on these 3 rotations and 3 boosts. So it really represents like these are really like accelerations of your frame. Okay? So it really depends. So this is why we say that this teleparallel spin connection represents only inertial effects, or that's what we mean by that, yes? Because just the choice of your frame or how you rotate it, how you boost it, gives you your spin connection. It's independent of the metric and of your space-time metric, yes? And then basically it turns out that this is equivalent to the most general Riemannian connection which you can have in Minkowski spacetime. Yes, because the most general tetrad in Minkowski spacetime which you can have is some local Lorentz transformation of this diagonal tetrad. Yeah, so when you calculate then Riemannian connection for this, you find out that this teleparallel spin connection of this form is a Riemannian connection of this reference tetrad, which is some Minkowski tetrad. And I will talk a little bit later, like how we choose this reference tetrad. Yes? I mean, this is like a little bit more complicated approach how to do it. You can also just think about it like you can start with a zero spin connection, basically do a local Lorentz transformation, and because spin connection transform non-covariantly, so then you will basically induce this connection there. So basically, what this means is you can also take it in the other approach. Since it's pure gauge connection, you can also find such local Lorentz transformation that transforms the spin connection to zero. And we usually say that there is a class of tetrads, which we call, for some reason, proper tetrads, in which the spin connection vanishes. Yeah? So we have some class of tetrads for which we can do this. And we call this, because of some historical reasons, nowadays people call it Weitzenburg gauge, because it corresponds to this Weitzenburg connection in some other formalism. And this is the approach which is often followed by many people. And it is a consistent approach, like if you want to obtain some results, but there are some small subtleties with this approach. The only subtlety is that you must keep in mind that if you start with this tetrad and a spin connection, you can always do this transformation, but you must understand that you basically are choosing like some kind of gauge here, which is okay, but you must be just aware of it. Because when you once choose this gauge, then you know, it's a little bit difficult to discuss like violation of local current symmetry. I mean, you chose already your gauge. And there's like one minor point. The second minor point is that it leads to some mathematical inconsistencies, because then you have such expressions in your theory, like this contortion tensor is equivalent to the connection. And this is a problem, because normally there should be a difference of two connections, which is a tensor, but here, since you say there is a zero connection, you have these equivalencies like tensor equals connection, and we know the connection is not tensor. So, but it still leads to a physical result for some reasons, for which I will talk a little bit later. So when we have this teleparallel geometry, this basically allows us to formulate some theory which is equivalent to general relativity, or reformulate general relativity in an equivalent form known as teleparallel equivalent of GR, where we basically reformulate general relativity in terms of torsion. So we take this quadratic Lagrangian, is constructed out of this TA mu is teleparallel torsion. So this really looks like some kind of like very nice Lagrangian, like some Lagrangian of some gauge theory. I mean, that's why this theory is so attractive. And you derive your field equations. Here should be a partial derivative. Partial derivative of this equals. So this looks very different from GR. Both this teleparallel Lagrangian and these field equations, they look very different from GR. But it turns out that they are completely equivalent to GR. Well, not completely. I mean, the field equations are completely, and the action is, there is some small difference. And how you show this equivalence with general relativity is that you can take this teleparallel spin connection and this Riemannian spin connection, and you relate them by this Ricci theorem, yes, which tells you that you can write any connection as a Leibniz connection plus contortion tensor. This is some permutation of torsion tensors, using which you can show that this Hilbert action can be written as a Hilbert action of general relativity, can be written as this teleparallel gravity Lagrangian, yes, so this thing here, plus some total derivative. Yeah? So basically, this teleparallel gravity Lagrangian is equivalent to Hilbert Lagrangian up to some boundary term. But since this boundary term, it doesn't contribute to the field equations, then it means that these theories are dynamically equivalent. And it means the field equations are completely equivalent. Yeah? So this equation, this left-hand side of the teleparallel field equations, although it looks very different, this is just equivalent to Einstein tensor. So it means that it also leads to the same field equations. Yeah, same solutions of those field equations. It's just another variables for Einstein equations. So it doesn't make much sense to be like doing solutions of these theories, because well, all the solutions are the same. You have the same Schwarzschild, same K, everything is the same, because this is just a different way of rewriting Einstein tensor. But where is the difference? It's in the action, because you could see that the action is not completely equivalent. It's equivalent up to this boundary term. And that's what I was saying at the beginning. Exactly all those problems in GR, they come from the boundary terms. I mean, they come from all those boundary terms. Yes? I mean, like from all those weird terms, this Gibbs-Hawking boundary term, and this regular, then you have to do this subtraction of the background, and all that is caused exactly by that total derivative term, which we actually in teleparallel gravity remove. But that's why it's an interesting problem to consider this problem of gravitational action in teleparallel equivalent of GR. This equivalence up to a surface term is very, very important, because the surface terms are very important. So if you just look on it like this, that the teleparallel gravity Lagrangian is basically Hilbert Lagrangian minus the boundary term, the total derivative term. This means that this Lagrangian contains only the tetrad and first derivatives of the tetrad. Right? So there is not any there is no problem with second derivatives of the tetrad here. So this means that we can define a variational problem. We can do a variation of this action, and we can just impose these Dirichlet boundary conditions. Yeah? Only the variation of the tetrad at the boundary must be 0. We don't have to add any Gibbons-Hawking or boundary term. And this Teleparallel Lagrangian is equivalent under simultaneous local Lorentz transformation of the tetrad and the spin connection. So, but of course, if those theories are equivalent, and we remove these problems of, removing this problem of the second derivatives and having Gibbons-Hawking your boundary term, like we couldn't just solve it miraculously. We have to, the problems are usually conserved. So we must have this problem somewhere else. And that problem actually appears somewhere else. But that's a little bit different problem. It gets translated into some different language. The problem there, well, it's not the problem, but we have this Teleparallel Lagrangian, which depends on the tetrad and derivatives of the tetrad, but it also depends on the spin connection. So it means we have to also consider some kind of variation, or we have to consider like how this theory depends on the spin connection. And then basically, the whole problem of regularizing the general relativity action, like the standard Einstein-Hilbert action, becomes a problem of how do we match the spin connection to the tetrad. And basically, this was my paper with José Pereira from Sao Paulo in 2015, basically where we argue that there is a very close analogy with Gilbert action plus Gibbons-Hawking or boundary term. Because it turns out that this, where you can see this analogy, is that the spin connection here enters the action only through the surface term. Yes? So, I mean, we can show this by some very small trick, that if you take this Teleparallel Gravity Lagrangian for the tetrad and the spin connection, you can write it as a Lagrangian just for the tetrad, plus some total derivative term, which depends on the spin connection. This also shows that the variation of the action with respect to spin connection is 0, because this is just a total boundary term. But of course, there is a big if, and your action must be actually finite. Right? Because if it is diverging, then actually these variations don't make any sense. But that's actually the point. We can add this spin connection term in such a way that it regularizes. So only in that case, when this spin connection term is actually regularizing your action, only in that case, this variation with respect to spin connection makes some sense. Well, also variation with respect to tetrad. And so this is the one aspect where is this similar to the situation in Gibbons-Hawking or boundary term. Because we have this dependence not only on tetrads, but also on the spin connection. This spin connection is some kind of boundary term. And also, what I have just said before, the most general spin connection can be always written as some kind of Riemannian connection of this reference tetrad. So basically, what we propose is that this Teleparallel Lagrangian, if you see it like a Teleparallel Lagrangian of the tetrad and a spin connection, and the spin connection now you understand is a function of just the reference tetrad, basically it has a very, very similar structure to this finite action, which we usually search for in a general relativity. But in general relativity, classically, you have this, it's like very ugly terms, yeah, because you have this Hilbert term, then you have these total derivative terms which you have to like cancel by this Gibbons-Hawking your boundary term and then subtract it. It turns out like you have to subtract this background. So here it turns out that all this you can somehow combine into one expression, which is of course a little bit equivalent to what we have, like what Gibbons and Hawking did in 1977. But here you have this quite weirdly, because you basically all the mention of this reference spacetime gets somehow incorporated into information about your spin connection, which is, I think, quite interesting aspect of of teleparallel gravity. Like, this is for me something new with respect to general relativity and something interesting. So basically, and it also shows you some physical picture. Like if you call this basically this choice of the tetrad and searching for such tetrad that regularizes your action, we can call it a teleparallel regularization of the action. So you can see some nice physical picture of this teleparallel regularization. Yes? Instead of finding this reference metric or tetrads and using them through this Gibbons-Hawking or boundary terms, we actually introduce them on the level of the spin connection and incorporate them into the torsion tensor. And then it turns out that you can also understand some physics of this, because we have this pure gauge connection, which is given really by these 6 local Lorentz transformations. So these are really your inertial degrees of freedom, in the sense that they really represent just the freedom to choose the frame or tetrad. Yes? So it's really the inertial effects in almost like a Newtonian picture, yes? Where there are these pseudo forces, yes? Which just tell you how your thing is accelerated or rotated. Yes, they're not physical forces. Yes? And also, because of this point, which you understand that they are not physical forces, yes, they don't have to vanish at the infinity. Yes? I mean, a nice picture of this, you can see if you have a rotating, we have a rotating observer, all his space-time is rotating, and everything in the infinity looks to be rotating and leads to some divergences. But you understand why, because this is just these rotations. So this is not a physical field, yes, just the rotation. This is just a fictitious force. And now you can understand that this is exactly what is causing these divergences of your action, because your action, this teleparallel action, is sensitive to these, let's call them inertial degrees of freedom. So since we have this freedom to choose the spin connection, yes, because I just said that it must be given by some reference tetrad, yes, or it can be calculated from some reference tetrad. But since it is not given by any field equation, we have some freedom. How do we choose the spin connection? And so we have this freedom, and you can use this freedom to actually regularize your action. So what you can do is you can choose your spin connection in such way that basically you just want your teleparallel Lagrangian to vanish at infinity fast enough. Yes, and if you require this, you will have your action will be finite. Yes, because you exactly want to remove this spurious divergences at the infinity, which comes from these rotations and boosts. And if you do this, yes, I mean, if you require this, then one of the solutions which you can have is, well, exactly what we had before. Yes? Like this equation is definitely satisfied if this torsion, and here I write for the torsion scalar, but if you write for the torsion, then this teleparallel spin connection can be defined as this Riemann connection of the reference tetrad. And the reference tetrad, in the case of asymptotically flat spacetime, can be obtained like taking your dynamical tetrad, your full tetrad, which describes your spacetime, and just taking its asymptotical limit. And of course, there is some. This is probably not always possible. This only works for some kind of asymptotically flat spacetimes. And for a long time, I was a little bit worried that, like, oh, how do we generalize it? But because this is not a unique procedure, and it's not even it's not applicable in each case. Yes? Like, for example, if you have like some asymptotically AD spacetime, this is like not easy to follow. And I'm working on it, like how to do it also in asymptotically AD spacetimes. But on the other hand, it's not such a big problem, I think, because yes, sure, we cannot completely always follow this method. But you just have to remember that we also cannot always follow this Gibbons-Hawking your background subtraction. Yes, this Gibbons-Hawking your background subtraction also doesn't work. in each case. Yes, and yeah, it's a known problem, but it's not, it's not lethal for your theory or for your approach. Yes, so this is something similar in teleparallel gravity. Yes, we have some method, but we cannot completely apply this method in completely each case, like arbitrary spacetime. But we should still search for some ways how to apply it also in these cases where this naive solution fails. So just to give you some example, it's just a regularization of the Minkowski spacetime. I mean, Minkowski spacetime is the easy spacetime which you can have in principle, yes? And it's kind of trivial, but in principle, it turns out that it's actually non-trivial to achieve this. It's trivial in an empty case, in a Minkowski spacetime, in a Cartesian coordinate system. If you take this Cartesian coordinate system, you actually find that this torsion tensor is 0 with the spin connection. So you have your torsion, like in Minkowski spacetime, you would expect your torsion to be 0. Yes, your actions should be 0 in Minkowski spacetime since it's Minkowski spacetime. But however, if you try to apply it completely naively in a spherical coordinate system, so you take your tetrad in a spherical coordinate system, you will find, and you don't know what kind of reference tetrad put here. So if you just take 0 naively, you will find out that this torsion scalar is 1 over r squared. So then action actually diverges, yes, because in action it will be multiplied by r squared sinus theta coming from the determinant of the tetrad. And that's constant. So then actually if you integrate it over your whole spacetime, you will find out that the action actually diverges. So it means that if I start with this tetrad, I have to put something different here. I have to put some spin connection which from some reference tetrad, yes? And in Minkowski case, this is very easy because, well, this Minkowski tetrad is your dynamical tetrad in some way, but your spin connection is, but you can use it, since it's Minkowski tetrad, you can use it as your reference tetrad as well. So it's kind of trivial because your dynamical reference tetrad are the same. You can do it only in Minkowski spacetime. And if you do it, you calculate the spin connection by the method which I showed you before. And you find out that even for this spherical coordinate system radial tetrad, you will find out that the teleparallel action for Minkowski is really 0. So that's what you would expect and what you want to have. It's a little bit less trivial in the Schwarzschild case. Yeah? So if you take a Schwarzschild case, because there we usually have to work with the spherical coordinate system. So I take this tetrad, given by this one minus, and if I would just test it with a 0 spin connection, you find the same problem, exactly the same problem. You'll find that this is 1 over r squared and the action is divergent. Now I can use the prescription which I did before, and I can take a reference tetrad, but now the reference tetrad is not this tetrad, because the reference tetrad must be in the Minkowski spacetime, but I can take this tetrad as a reference tetrad and calculate the same spin connection as I calculated before, and use this spin connection together with this dynamical tetrad. And when you evaluate it, you will find that Euclidean action is actually finite, and actually very, very finite and physical. Sorry, here is a mistake. Here should be the time integral of n. So this action should be the time integral of n, which is exactly what you want, and exactly what you actually obtain. By the background subtraction using the Gibbons-Hawking method. So now, this is still like some of my old work, but now what is the new work here in this presentation? It has something to do with with the question like how unique is this determination of the spin connection using this reference tetrad. What I mean by that is not whether I can, as I told you, it's not clear like how to apply it in a completely general case. We don't know how to do that, but we don't know also how to do that with Gibbons-Occhio boundary term. So how do we? But the question is, if I have some problem, like let's say like this Schwarzschild problem, which I just showed you, and I have this problem and I know how to calculate the spin connection, how unique is this determination of the spin connection? That's like interesting question. Because as I told you before, yes, I can show that this spin connection enters through the surface term. And in principle, you have 6 local Lorentz transformations. There are only these 4 components of this, and even then they are traced over this divergence. Yeah, so the question is, how unique? Is there some freedom in this determination of the spin connection? Yeah, because it's obvious that I have a lot of freedom to do 6 local Lorentz transformations, and there will be always some 6 local Lorentz transformations which will not change this total derivative term. Yes, because total derivative term is very, very simple and it's just one scalar function. Yes? So the question is, like, how do you? So what is this freedom? Yes? There is always these local Lorentz transformations which keep this boundary term invariant, and we call these transformations so-called remnant symmetries. I mean, this is in his non-covariant formulation, where they are the symmetries of your action when you transform the tetrad. But you can have something like equivalent to this in this covariant formulation, which I'm using here. So basically, you can say that there is a class of local Lorentz transformations that do not change this and do not change the boundary term. And they play some role, and they show you, they play some role in a general relativity, in this teleparallel equivalent of GR. Yes, because this paper by Ferraro and Fiorini in 2014, they were discussing this in these modified theories of gravity, because in this modified FT gravity, this becomes very important because it has some consequences for the dynamics of your theory. But my point, which I'm trying to make here, and that's my upcoming paper, which I should have soon out, is exactly about this. It's about that there is some role of these remnant symmetries in this teleparallel equivalent of GR. Yes? They are the symmetries of these boundary terms. They are the freedom which you can do. They are the freedom of changing your spin connection in your theory in a such way that no physical quantity gets affected by that. So they are a very important symmetry in teleparallel gravity. And if you want to do them infinitesimally, it turns out to be quite simple. Just take a variation of this boundary term, and infinitesimally it will be just given by this expression, yes, where you have this tetrad, and this will be the 6 local Lorentz transformation. And what you will find out is that you can do it for Minkowski and Freeman-Robertson-Walker. And in Minkowski and Freeman-Robertson-Walker, this was already done in the paper in 2014 by Ferraro and Fiorini in the context of FT gravity, but that's kind of, in this case, it's similar to teleparallel kind of GR. And in Minkowski case, you find that that's equivalent. Minkowski case, all 6 local Lorentz transformations are this remnant symmetry, so they are really a symmetry of your problem. I mean, you can see it very simple from this, yes? I mean, in a Cartesian coordinate system, it will be very simple, because in Cartesian coordinate system, these are just constants, so the partial derivative of these constants will be 0, and then basically all symmetries, all boosts will be symmetries, yes? So that's quite easy. It's less clear to see it in a spherical coordinate system, but it turns out to be the same. So it means that you can do any of the 6 local Lorentz transformations. You can do 3 boosts and 3 rotations, and your action will be not changing. In Freeman-Robertson-Walker, it's already a little bit different. When you consider this, the Cartesian coordinate system, yes, you will find out that this change of this boundary term will be given by this expression. Okay? So what does it mean? Is that infinitesimally, it means that there are no rotations. So it means that you can do all three rotations, and these all rotations, they are the symmetry. But then these three boosts, there are these three special boosts, this 0, 1, 0, 2, and 0, 3. Yes. And if the 0, 1 depends, yes, so this is like 0x, if it depends, but it's there's a covariant derivative of I. If it is a function of x, then it turns out that it's not symmetry anymore. But all boosts in an x direction which depend on other coordinates will be symmetries. So you see that remnant symmetry in this Minkowski spacetime is all rotations and these three special boosts, which depends on all other coordinates except the direction in which the boost is performed. So what is new in this presentation compared to that Ferraro and Fiorini paper, is that and will be in my next paper, as that I have now also solved this problem for the spherical symmetric spacetime. So if you have a spherically symmetric spacetime, like this, like in a Tegger case, this can be for the Schwarzschild solution, but this is even more general because it's very easy to do it in this most general case of the spherical symmetric spacetime. And you have this spin connection, the same as in Schwarzschild. You can look how the action change, how this boundary term is changing when I'm doing just these local Lorentz transformations of the spin connection. And what you will find out that this change of the boundary term is given by this expression. It's a little bit complicated, but actually if you look on it closely, it means that all time you have these boosts, only the time derivatives of all three boosts. So it means that all time-dependent boosts are actually changing the action. But it also means that all three time-independent boosts, they don't change this boundary term. They don't change the action. So it means that three time-independent boosts are actually this remnant symmetry. They are the symmetry of the problem. And also, these kind of I still haven't figured out completely what it is, but this is some kind of special rotations. I think this is some rotations around some axis in a coordinate, in some spherical coordinate system. So this is probably some weird rotation around some axis. But you can see that these are some three special rotations. They are not full rotations, but some subsets of these rotations are also the remnant symmetry. So my point is that this was just an example, and I just want to show you like one important property of this action and why I think it's interesting. It's because this was for the infinitesimal symmetries, but I can construct a finite transformation by just doing exponential map. Yeah? So even though these are my expressions here, yes, for example here, where they hold just for the infinitesimal transformations, I can do exponential exponential map of these infinitesimal transformations and construct finite transformations, because usually we are interested in finite transformations. And I can show that all these transformations which were symmetries here, also when I do their finite counterparts, remain symmetries. So it means that if I take time-independent boost, like some finite time-independent boosts in the r and in theta direction, they will be symmetry, like full symmetry, non-infinitesimal symmetry. So that's quite nice. But then when you try to combine them, some interesting property of these remnant symmetries gets revealed. Because it turns out that they do not form a group. Yes, because in physics, at least in such classical physics, when we usually deal with symmetries, we usually deal with group symmetries. Yes? I mean, group has some mathematical properties. And one of these main properties is actually a closure axiom. Yes? A closure axiom means that if you have some element of, so you have some element of your group, and then you have some second element of your group, the combination of these two elements is a member of the same group. Yes? So it means that, for example, like if I do one rotation in x direction and the other rotation in the second direction, this is equivalent to rotation in some third direction. Yes, because that's how it works. So it means that if you look on, like let's say, group of rotations is actually closed, so it's a proper group. Right? But if you look, for example, on boosts, and you ask, do boosts form a group or subgroup of local Lorentz transformations? It turns out that no, Lorentz boosts do not form a group or subgroup of local Lorentz transformations, because if you combine two boosts, the result is not another boost. Yes, the result is another boost times some rotation. So because of this, it means that the Lorentz boosts, they are not closed, so they do not form a subgroup. And something similar happened here. And this mathematical concept of, and you have all the properties of the group, except this closure axiom. This is something what is called groupoid. And you have these Lie groupoids and Lie algebroids. And it's usually applied in some very, very fancy parts of mathematics. I've seen it somewhere in string theory and in non-commutative geometry. Usually, I've never seen it being discussed in the context of general relativity or some gravitation theory, like a classical gravitation theory. But actually, it turns out that it's exactly the property which you have here. So it means that if you take two symmetries, two these remnant symmetries, they will not form a group. Yes, there will be not a transform. There will be not a symmetry. You combine two remnant symmetries, the outcome is not a remnant symmetry. But it has all the other properties. You have some like inverse elements, so that's why this remnant symmetries, you shouldn't talk about remnant group of symmetries, but remnant groupoids of symmetries. And I think it's quite interesting, and it's quite interesting that such mathematical concepts appear here in teleparallel gravity. And just to show you that this is something actually, because usually when I have seen this first time, I was like a couple of weeks or months looking like, what are groupoids and how should I understand them? That's usually not the thing which we do in GR, but, and I still am studying them. It turns out that you can do a lot of mathematics, like conversation laws, also not only with Lie groups, but also with Lie groupoids. And I think that's something what is happening here. So that's what my current research is about. And for example, in this Minkowski spacetime, you can see the simplest example in the Minkowski spacetime. Right? Because if you take the Minkowski spacetime like this, with this spin connection, so this leads to a, like this is a spherical tetrad, or the tetrad in a spherical coordinate system for the Minkowski spacetime. We know how to calculate the spin connection for that, and it leads to a zero action. We know that, as I told you, all local Lorentz transformations are the remnant symmetry. Right? So it means that you can do all 6 boosts and rotations, and they will not change this zero action to anything. But actually, what if you take these 2 Lorentz transformations? And it turns out that that's exactly how this thing is calculated. Because this spin connection, is given here, is calculated because there was this expression like it's a pure gauge connection of some local Lorentz transformation. The local Lorentz transformation which is there is actually the combination of two rotations, and it's rotation metrics around the y-axis by the angle phi, and the rotation metrics around the z-axis by this theta minus pi half angle. I don't know why exactly this, but that's what you get. This you get that this local Lorentz transformation is the one which is generating the spin connection. That's how we calculated it. But you see, each of these rotation is a remnant symmetry. But this combination is not a remnant symmetry. Yes, because that's exactly the thing which change our action from the divergent action to the zero, to this regularized action. We regularize this action by doing the local Lorentz transformation, calculating spin connection from this local Lorentz transformation. But if you do just one rotation by any of these y, z, or by any angle or anything, they will be a symmetry. But their combination will be not a symmetry, and they will be changing this action. So that's quite an interesting example of these remnant symmetries. And they have some quite important consequences for our understanding of what is going on, and not with just teleparallel gravity or modified gravity, but also what is going on with gravity itself, I think. Because this is very important property, this uniqueness of the action. Yes, it's a very, from my point, it's a very important insight into the nature of the gravitational action. And there is a lot of this nice new mathematics which is just popping out, like exactly like this, groupoids and algebraids and all this kind of stuff. And while usually when I see some purely mathematical literature, at least for me, is usually such high concept, which is quite hard to follow. But here you see all these concepts be appearing in some very nice, easy context, exactly like rotations in Minkowski space-time. You can start to see this very high mathematics, which I think is really fascinating. Then, so that's one point. That it has some very important understanding for the uniqueness of the action, but it has some important consequences for the conserved charges. Yes, I think that there is a lecture done Tuesday and Wednesday afternoon by Sergio. I mean, he was talking Portuguese about the conserved charges, but basically the conserved charges, they are derived from the action. Yes, and so this also means that these symmetries, these remnant symmetries, they show you like how unique is your determination of your conserved charges as well. Yeah, so I think these remnant symmetries, they play quite an important role for the conserved charges. They show that some redundancy in some kind of broken or non-broken gauge symmetries in determination of your conserved charges. And of course, it's important in modified gravity, and mainly in FT gravity. This is actually where Ferraro and Fiorini in 2014 were first starting to discuss this. And I mean, they were considering this problem in FT gravity. Because in FT gravity, it becomes even somehow more pronounced, this problem. Because here, it's just something to do with the action, but it doesn't affect the field equations. But in FT gravity, this becomes a problem of dynamics. It becomes a problem because these remnant symmetries, there will be the symmetries of your problem, but all those other local Lorentz transformations, which will be not in this Lorentz, in this remnant groupoid, yes, they will be kind of broken, and they become propagating degrees of freedom in your theory. So that, I mean, that's why they were studying them. Yes, I mean, that's what is interesting about it. And here comes the important that point which I just made, that this what I'm trying to show in this talk and my next paper, that why it's important, for example, to consider this like that the remnant symmetries are not group but groupoid, because if they are not group, then it's very hard to understand the dynamics. Yes? Because normally what I would expect is, like, let's say, I mean, there's still this discussion whether FT gravity has 3 extra or 1 extra degree of freedom. As these extra degrees of freedom in FT gravity, they come exactly from this Lorentz group, from the breaking of the Lorentz group in this non-covariant formulation. Yeah? But this shows that if they don't form a group, and you can have some like you can have one boost, another boost, they are symmetries, but when you combine them and they are not a symmetry anymore, that's something very weird and makes the dynamics very hard to understand, and makes probably it's potentially a very big problem for FT gravity. It also shows that then it means that these remnant symmetries, they will be strongly depending on the theory. Yes? Like in FT gravity, it will be different than in some NGR or in some other theories. I think that's also quite an interesting aspect. And this is potentially a big problem for all these modified teleparallel gravity theories. Mainly this non-group character. I somehow have big problems how to reconcile this with any meaningful propagation of any degrees of freedom. So basically, how long? Okay, so I'm talking more than 1 hour. So basically, the summary of this talk is that although this, like in recent 10 years, the main focus in this teleparallel gravity was mostly on these like modified theories of gravity, particularly FT gravity. There is still a lot of interesting things going on in teleparallel equivalent of GR itself. And particularly when you start to look into places where you can see some difference. Yeah? Because the field equations are the same as Einstein field equations, so you can't see any new solutions or anything. But when you look, for example, on the action and some properties derived from the action, you can start to see some difference and some new interesting aspects. So basically, I think that's like one point of what to do. Yeah. So, and what I was trying to show is that general relativity, when you just take a Hilbert action, it has some problems, and it took a long time to solve this problem, to have this Gilbert-Hockling boundary theorem with this background subtraction. And there's still a lot of discussion going on about this. And the teleparallel gravity actually offers really nice insight into this problem, since it allows us to have consistent variation principle with Dirichlet boundary condition, and it somehow allows us to do kind of the same background subtraction, but it allows us to do the background subtraction of kind of on the level of the connection. So we don't have to go through all this. Somehow incorporate this reference spacetime, this reference tetrad, on the level of connection, and we regularize the action. And I think this is quite interesting. And potentially it has some consequences for our understanding of GR itself. And this, another problem which is related to this is exactly the remnant symmetries. Is if you start to ask how unique is this procedure of the regularization of this action in this teleparallel picture, you will start to see that these remnant symmetries start to pop up. And they have these very curious and fascinating properties, exactly like that. They seem to form groupoids and not groups and something similar. And something like that has some consequences for FT gravity and other theories. And I start to fear that it's potentially lethal for most of these modified theories of gravity, or teleparallel modified theories of gravity. So anyway, I will have, I hope soon, I mean, I'm keeping saying that for a long time, but I hope soon I will have some paper, like in a matter of weeks, I will have this paper out where I will explain this. But still, there is it seems that there is a lot of research needed, and a lot of new things start to pop out here, and there you can start to take this research in many new directions. when you just start to look on this action and try to understand the properties of these Revlon symmetries and non-Revlon symmetries. And the problem of the symmetries of this action is actually a really fascinating problem. So I think people should follow it. Okay, so thank you for your attention. And I think that's it.
Thank you, Martin. Now we pass for the questions. And we have a couple of questions here. The first question is from Lucas Santos. He writes, is there any physical interpretation for these coefficients of anholomy? Where do they come from?
So the coefficient of anholomy, you mean here, yes? So like this here, yes? So basically, this is like normally like how you derive this, yes? These crystal symbols. This is just a connection when you work in the holonomic basis, yeah? So in the coordinate basis. So in a basis which is commuting, yes, because that's exactly the definition of the coordinate basis. It's such a basis which is commuting with each other. So if you have a basis vectors, if they commute, it's holonomic. It means you can work in coordinates. And if you start to do differential geometry, the Riemannian geometry, you will find these crystal symbols. The point of tetrad formulation is exactly that you work in an unholonomic basis. An unholonomic basis is exactly defined by the fact that if you take two basis vectors, they don't commute with each other. So this coefficient of unholonomy, that's actually just the commutator of two vectors. Right? So that's your coefficient of unholonomy. That's the commutator of two vectors. And when you start to do differential geometry, you will find out that your connection is expressed in terms of these coefficients of unholonomy.
Yes. We have another question from Lucas Santos. Professor, do you think this kind of position, the scientific community, let me write again. Professor, do you think this kind of position the scientific community had at the time, stimulated Einstein to abandon the teleparallel approach?
Well, the problem of Einstein in like 1928 was he was trying to somehow put there this electromagnetism, and simply there is no electromagnetism. Yes, I think I'm trying to read some of these original papers, and I still don't completely understand like where did he see the electromagnetism coming in? Yes, because there is obviously nothing. Yes, but I think he was just basically motivated by this fact that, you know, like a metric has 10 components and tetrad has 6 extra components. These 6 extra components, they have something to do with like Faraday tensor or something like that, right? Because Faraday tensor has 6 components. So he was trying to see there some connection. But so his motivation was actually like very, I mean, he was doing something very wrong in principle. Right? I mean, his motivation was wrong because he was trying to do wrong stuff, yes? But of course, it's Einstein, so usually the Einstein does some blunder also with cosmological constant. Then usually people in a couple of decades discover that it's maybe not such a stupid thing. But sure, it's a similar thing, like exactly like with cosmological constant, yes? Like he introduced cosmological constant to make, you know, static universe. And of course, that was a wrong motivation and it failed. But then people discovered couple of decades later that it has some meaning. Yes, it was actually a clever idea. And same thing here. He was doing something with the wrong motivation to like unify gravity and electromagnetism, which was wrong. So of course it failed. But then people like Muller and later in '60s discovered like, oh, okay, he had a basically he made another formulation of general relativity, and that's interesting.
Yeah, maybe in some decades we discover that teleparallel gravity is really electromagnetic field.
I really doubt that.
Well, Martin, I believe we don't have any more questions here, but I have a question for you.
Okay.
What is the difference between Einstein-Cartan formulation and what you presented? Because in Einstein-Cartan theories, we have the connection different from zero, and you proposed a gauge where you have exactly something like that. So what's the difference?
Well, in Einstein-Cartan theory, yes, well, you must be careful what you mean by that, but if you mean this Einstein-Cartan schema-Kibble theory, yes, because Einstein-Cartan geometry is a general geometry where you have both curvature and torsion. Okay? And then there is a question like, how do you, if you want to make a physical theory out of this, yes, like a physical field theory, it's not enough just to give you a geometry. You also must put some like field equations or Lagrangian. Yes? And usually when people do this, they mean this Einstein-Cartan schema-Kibble theory, which basically starts with the action. It is the same action as Einstein-Gilbert one, so just a scalar curvature. But you see, there is already a problem because that Einstein-Hilbert action is actually not a correct action. Yes, I mean you need all these problems, Gibbons-Hawking or boundary term. But okay, they start with that, but then they say this scalar curvature there is not a Riemannian curvature, but it's this Einstein-Cartan curvature. Yes, and then they do vary the action, and they obtain some theory which is different if you have some spinning matter. Yes. So in that theory, as actually this Einstein-Cartan schema-Kibble theory is a different theory because you have still a curvature there, and in a case of spinning matter like some fermionic matter, you start to see some difference with Einstein gravity. So only in the presence of matter you see some difference with Einstein gravity. So it means that also this effect of torsion there is somehow like an addition to curvature, and it represents some additional degrees of freedom which are there, like addition to curvature. Yes, so that's different in teleparallel gravity, because in teleparallel gravity basically your torsion takes the role of curvature. Yes, you don't have any curvature in your theory. It still plays some role in curvature because the zero curvature gives you some strong restrictions on your connections and on everything. But in your field equations or anywhere, the curvature doesn't appear. So this theory is equivalent to general relativity, only like kind of rewritten in terms of torsion. While Einstein-Cartan schema-Kibble theory is a different, physically different theory, which has different predictions for some dynamics.
Okay. Another question, I have a couple of questions for you. Another question is, what's the motivation to introduce a connection different from zero? Because if you want to introduce local Lorentz symmetry, you just consider the divergence in the Lagrangian, and your Lagrangian, even in teleparallel gravity, is still invariant under local and global Lorentz transformations. So what's the motivation to consider local Lorentz transformations into the connection?
What do you mean that it's invariant? Like if I have...
Yeah, you write the Lagrangian. See, Lagrangian of the Teleparallel gravity, please.
Yeah. So you have this, yes. So this thing, you mean like when I put the spin connection to 0?
No, not this. Sorry. When you write the scalar curvature in Riemannian geometry, you have R equal to a combination, exactly, the scalar of torsion. So if you add a divergence of torsion, for instance,
you mean like if I add this, yes?
Yes, if you add this, your Lagrangian is invariant and is exactly under the same symmetries of general relativity. So
yeah, it is. Yeah.
So why not just to consider a Lagrangian like that instead of going to the connection to add this another symmetry? My point is, what's the motivation to put into the connection and not into the Lagrangian like this?
Well, it's just the other way, but basically that's why I was doing this long introduction here. I was trying to show you, yes, that this action, this Gilbert action, yes, which is just the scalar curvature of R, it's actually not a good action, yes. I mean, that action has this problem with this extra boundary, these extra surface terms, and we have to, if you want to have a consistent variation principle from Hilbert action or Einstein-Hilbert action, you have to add this Gibbons-Hawking or boundary term to cancel this variation of the surface of the boundary term, or this total derivative term, and then you have to like regularize it by this. So the idea of teleparallel gravity is that we can take a shortcut, guys. Like, sorry, where I am, guys. So this term here, the point is that this Lagrangian is not a correct Lagrangian. This Lagrangian must be supplemented by all these Gibbons-Hawking boundary terms and this subtracting and this regularizing subtracting terms by these counter terms. So the point of teleparallel gravity is exactly that I can formulate a consistent Lagrangian, yes, which is given just by this consistent Lagrangian, which is basically equivalent to that Hilbert Lagrangian minus all those bad terms which people like Gibbons and Hawking were trying to remove. And so in this, if you look on this from this perspective, my point is that teleparallel Lagrangian is actually coming without all this mess with the boundary terms, at least superficially. Yes, you don't have to add there anything, but you have to add something, and that something is the spin connection.
I see.
So my point is that the Hilbert Lagrangian is not the correct Lagrangian. The Hilbert Lagrangian must be regularized by this unnatural way. So if we can do it in other clever way from teleparallel perspective, it's just a new way of doing stuff, and maybe we can do something with that.
Yeah, but the Hilbert Lagrangian leads to the Einstein equations, which is the correct equations for gravitational field. So why not focus on this kind of Lagrangian?
Because okay, there are two answers for that. Because as I said, okay, the first simple answer is if you add, like, if you start to do your teleparallel gravity like with this teleparallel Lagrangian plus this term, yes, you are basically doing, I mean, it's just a GR. Yes? I mean, you just basically, I mean, in GR everything depends on this Riemannian spin connection, yes. So basically, you take your Riemannian spin connection and you just write it as a teleparallel connection minus contortion, and you just rewrite everything in terms of this. But there is no way of finding any new effect of anything because you're basically just rewriting everything completely equivalent. Right? I mean, that's one way of saying it. Like, if you want to see something new, you have to do else, at least something you have to change, yes? And the change for me is exactly that I'm taking the Lagrangian of classical GR up to a boundary term. And that up to a boundary term can give me some new insights. If I include a boundary term, well, it will be just the same as in GR, right? So that's like one answer. And the second answer is like, that was this introduction about, right? That yes, Hilbert action, as I said, this is like very subtle issue, but yes, Hilbert action leads to this leads to this variation, which is exactly equivalent to from where you obtain Einstein equations. Yes, like if you set this to 0, you obtain Einstein equations. But since we have these boundary terms, you have these extra boundary term, and in principle, if you want to have really well-posed consistent variation principle, this Hilbert action doesn't lead to a consistent variation principle because you have to require at the boundary that this variation at the boundary of the metric vanishes, and also to cancel this term, you have to require vanishing of the derivatives of the metric at the boundary. And this is not consistent because there is a problem. This is like requiring both Dirichlet and Neumann boundary conditions at the same time. And usually you should have one of the boundary conditions, not at the same time. Usually at the boundary, you shouldn't send the variation and also derivative of the variation to 0. So this is the problem, and this is usually not considered, like mainly when you have like, I don't know, your introductory GR or even a graduate GR, this is usually not considered. People usually ignore this stuff, yes, this term. Because, and it took actually 50 years or 60 years to solve this problem because the solution is from 72 and 77. The people show that you have to add this boundary term here. Right? So if you really want to have a consistent variation principle, and consistent variation principle is mean deriving Einstein equations with the only Dirichlet boundary condition, then Hilbert action is actually not a correct action, and you must have a Hilbert action plus Gibbons-Hawking or boundary term.
Yes. So, do you think that the Lagrangian have to exhibit the same symmetries of the field equations, or maybe we can have some hidden symmetries inside the Lagrangian? Is not so clear. What is your position about these symmetries I mean, specifically in Lagrangian of teleparallel gravity?
Well, yeah. So in this like formulation where you have both this tetrad and the spin connection, this covariant formulation, yes. If you are like simultaneously transforming both of them, everything is locally Lorentz invariant. Right? But then actually you can start to consider like exactly this problem, since your spin connection is not determined. As I told you, it's given by some reference tetrad. Then it means like you can start to ask like, oh well, what if I just vary that spin connection, right? Or I just vary my tetrad, because that's what I have to do. When I'm trying to match my tetrad to the spin connection, I have to vary only one of them, yes? Because I mean, if I vary at the same time, I'm transforming both tetrad and the spin connection. Well, everything is covariant, and
I don't find formulation.
Yeah, I don't find any. No, Palatin formulation is actually different, but like here, when I'm doing just the transformation, yes, when I transform everything at the same time, then everything is covariant, and you don't obtain anything new. I mean, you obtain something, but you don't obtain. It doesn't tell you like how to match your spin connection to the tetrad. So you have to consider these variations where you vary them separately. And in that case, it turns out that's like that the field equations have this symmetry. That the field equations have exactly the symmetry that if you vary them independently, the field equations are insensitive to these changes. Right? But exactly if you transform only spin connection, the action actually changes by this boundary term. So you can see that field equations have definitely, I mean, they are definitely covariant in both senses, yes. And you can see that there is some stronger symmetry from that point, while the Lagrangian on itself has only this quasi-symmetry. So there is something different, yes. I mean, that's also the point why you shouldn't just add this boundary term, this divergence of the torsion vector, yes, because, well, then everything is the same as GR. So I mean,
yeah.
Then you cannot find anything new. I mean, that's, I mean, the point is, we still try to find something new, yes. So.
Questions here, just. So, Martin, I would like to thank you again for this fine presentation. I think it was very good for our audience, and people enjoyed very much. And I hope to have you in other opportunities. And I thank you again.
All right, thank you. Thank you very much for inviting me.